Go.
So today we're going to look at we have 4 balls, 4 ramps. Maybe kind of hard to see this, but we have 4 ramps here. And what I want to know is a couple things. One is which ball we're going to have a race. I love races. So which is going to get to the end of the ramp first? This ramp, that one, middle one, or the very end one? We're actually going to flip this around to the camera. So is it going to be the red, the green, the yellow, or blue? The colors don't matter. Which ramp do you think will have the ball moving the fastest at the end? Okay. If you need to, you can get closer for a moment. Take a close-up of this thing. So we're going to start 4 balls, all the same mass, all the same size. From there, I'm going to say 1, 2, 3, 4. And which one is going to hit the ground first? Okay, now I have a second question. Which is going to get to the end? Which is going to be the fastest ball? Okay. All right. Have you made your predictions yet? If you haven't, pause and think about your predictions. We're about ready to go. Okay. Jen, can we see the end as well without panning over?
We can see the end, but we can't see the meter after.
Perfect. Okay, on 3, we're going to let them race. You guys ready? 1, 2, 3. All right, so the question is, why was this one the winner? Why was this one the loser? Now, before I even answer that, let's talk about the actual speeds. There's another question of which one do you think was going the fastest? So take another pause and talk about, if you're somebody else sitting next to you, which one is going fastest off the ramp, and why do you think it was going fastest off the ramp? Pausing and unpausing.
Okay.
I'm going to have Jen actually pause for real.
Go.
Okay. So what we found out is this was the slowest. Well, first what we found out is, if you notice, all the balls, if you need to go back and rewind the video if you like, but all the balls landed in this little box down there. They all went the same distance. And they're all from the same height, so if they're the same height, it's the same free fall time, the same distance. So what does that mean about their speed coming off the ramp? That means they all went the same speed because they landed in the same spot. They didn't all come off at the same time, but they all came off at the same speed. So let's talk about that first. So why did they all come off the same speed? Well, so a common question you're going to have when you see an AP question is, well, how do I solve this? What problem-solving strategy do I use? Is this a law of conservation momentum problem? Is it projectile motion? Is this a work energy thing? Well, anytime you see a height involved, a change in height, that's a clue you're going to use the law of conservation of energy. Because the only energy we started with, every ball has the same mass, and they all have the same height above the ramp, so they all have the exact same starting potential energy. That means they all have the exact same kinetic energy coming off the end of this ramp. That means they have to be going the same speed, and they're going to land at the same spot. So that's one way to figure out the speed thing. But now, why was this one last? If they get all to the same speed, why don't they have a tie? Well, they got to the different speeds at different times. The far ramp to you guys, it had a greater acceleration at the beginning and almost no acceleration at the end. So that's why it came off first. It was at its top speed way before the others. This last one had these very small acceleration, great acceleration at the end, but the other balls had already cleared the ramp by the time this got to the bottom. So they all had the same change in height, gravity did the exact same work on every single ball. They all had the same gain in kinetic energy, but this one got there last because the acceleration was at the end, not at the beginning as in the first ramp. So to wrap this up, so if you want to find the velocity of the balls, because the projectile motion problem is what I used. So what I used is the displacement per time. But it's a horizontal displacement per the time to travel that distance. Well, all the balls landed 0.56 meters from the end of the ramp and went sideways. That's where the little box is on the ground, is at 0.56 meters. And they all took 0.38 seconds at the ground because that's that y equals 1/2 at squared thing to find the hang time in the air. And the hang time in the air, by solving for the t over here, because initial velocity downward was 0, you solve for the t and you find it to be 0.38 seconds. So 0.56 divided by 0.38 seconds is they all go in 1.47 meters per second sideways, not downward. That's a horizontal velocity only. Now you might be asking yourself this question, why didn't that dude just use the law of conservation of energy, the mgh 1/2 mv squared? That's what we were doing last week. Well, I could have. I don't have to know the mass of the balls because the potential at the top is the same as the kinetic at the bottom, so that cancels out. So as I solve for the velocity, so the 2 comes over on top, 2gh, you do the square root of that, it's 2 meters per second. You might say, what is up with that? You just found it's 1.47 meters per second. This says it's supposed to be 2. What's the difference? Is there an external force doing negative work to slow it down? No. The problem is there's more than one kind of kinetic energy involved here, and that's what you have to be careful of. There's also rotational kinetic energy. Because there's friction on the ramp, it causes it to rotate. And because it's spinning, the ball is spinning, it actually has kinetic energy just because of its spin. And we haven't learned about how you do rotational kinetic energy. That's still over a week away. So that's why I didn't use this to solve the problem, because I knew the ball was rolling, and this is the linear kinetic energy. So in a couple weeks, you're going to learn about how to do the rotational kinetic energy along with the linear kinetic energy. Those two added together, we would have found the velocity is about 1.5 meters per second. So that's a little primer on what's coming up in 2 weeks. I know you may not have been excited about it, but that probably gave you all the excitement you need, the anticipation needed to learn about rotational stuff coming up starting next week with torque. Have a great weekend.